Want to eat? Come. Lawan? What is it bad? Oh, oh.
Hello. Bro, yo, yo, yo.
Did you take the yeah? In the morning, you not spend in the evening. I always come to spend the night. I always ask you someone pray for me, and when I go to school, I always say can someone pray for me. Can you pray for me now? The house is getting distracted. You bring it up to her. Maybe.
Waterfall, you see me from a hill. Places in my arms, wonder why you feel me, feel me, feel me, feel me, feel me. I'm always gonna dive in where you are. You feel me, feel me, right? Touch me your way, stars on the lake look like $1,000,000. Let it wash all over you. Treat your body like a river. I see you coming at me like a wave. Yeah, yeah. Touch me your way, stars on the lake look like $1,000,000. Let it wash all over me. Waterfall, you see me from a third eye point of view. Oasis in my arms, my wonder why you fit me right. You fit me right. I won't lead us down. Your face is like a full universe. I'm always gonna die where you are. You fit me right. You fit me right. I lay your grace on me. Hallelujah, you amaze me when she walks away. That's my baby. She put. Oh, shoot. Let it wash all over me. Touch me twice, I make a line. Let it wash all over me.
What happened? This happened so fast. Why?
Petting the dog. He's so cute. Spent so much time on this question 5.
going to be oxidized. In the process, our fatty acid will be reduced. Bring in another protein that we added fats and opposite synthesis. Fatty acid synthesis to compare to initiate reduce unit G, including their location, the coenzymes needed, any energy needed, carrier protein. And since this is another reduction, we're going to require another NADPH to get oxidized. So a total of 2 NADPH to reduce this double-bonded oxygen down to a series of single bonds here. And now we're just going to repeat that. We're going to shift these 4-carbon guy to our fatty acid synthase to another portion on the enzyme. And we're going to bring in another malonyl ACP. So here is our 4-carbon guy attached, shifted to a different portion of the enzyme, and malonyl coming in into that acyl carrier protein site. And we're going to repeat it. We're going to get rid of carbon. We're going to connect to our 4-carbon unit here to this 2-carbon guy and lose this carbon as carbon dioxide. And then we're going to do our 2 reduction steps, and that's going to cost us a couple of NADPH. And so now we weigh A, attach carbon of an unfavorable set. A little bit less energy because already can things so that we could go back here is minus to go, which is going to attach in here. One of these atoms, saturated fat is basically the same. So unsaturated fats are actually going to give us a little bit less energy because the creation of that double bond, the oxidation there, reduced an electron carrier for us. And if we don't have to do that because the fatty acid already contains a double bond, we're going to miss out on that FADH. So a little bit less energy from an unsaturated fat, but in the big scheme of things, still not super significant. We're still going to generate a lot of energy from fat molecules. Let's summarize what we talked about in this video. And we create an NF going to sky. This would be the because they don't use electron carrier a coenzyme A to the fatty acid. This is going to cost us a couple of ATP to kind of get things going here. So a couple of ATP coming in there. And then we're going to move that activated fatty acid into the mitochondrial matrix, where we're going to break it down 2 units at a time, 2 carbon units at a time. And if you look here, this guy here with its 2 carbons is basically an acetyl-CoA unit. So the idea is we're going to break that thing off, and we're going to put the acetyl-CoA into the Krebs cycle, also which occurs in the matrix, and generate reduced electron carriers for us. Let's take a look at this data oxidation process in a little more detail. Here's our activated fatty acid, and the first thing we want to do is to oxidize it, and we're going to add this bond here. We're going to basically remove a couple of hydrogens and generate a double bond. So the enzyme we're going to use to do that is called a dehydrogenase. When you oxidize something on here, we're going to kind of double bond molecule of imagine us, which is going to attach to CO. We're just going to imagine that for a moment. If you've got a coenzyme A here, now you have 2 units that look awful similar. You've got this guy here, you've got this guy here, and so we're just going to break them. We're going to break them right there. And what we end up with is a 4-carbon unit with a coenzyme attached and an acetyl-CoA that can now go into the Krebs cycle. So we've got a couple of steps here in this thiolase, which is going to attach to coenzyme A and break the molecule in half. Not really in half, but break off the 2-carbon guy. Now this 4-carbon structure can now re-enter the cycle. You can see it's already essentially an activated fatty acid. It's just 2 carbon shorter. So we're going to take this guy and put him back up towards the step and repeat it. So oxidize it again. Create the double bond. Put the oxygen on there. 2 oxidation steps are going to generate us a couple of more reduced electron carriers. And then split, in this time really in half. And we're going to end up with 2 acetyl-CoA units at the end. So notice here, we created 3 2-carbon units. We started with a 6-carbon structure. And we created 3 2-carbon units. But we only went through the cycle twice. Because once you get to the 4-carbon stage, this guy only has to go through 1 more time to create 2 units. We don't have to put one of these 2-carbon guys through the cycle again. So the number of times that a fat is going to go through the beta oxidation cycle is 1 less than the number of 2-carbon units it can produce. If this guy can produce 3 2-carbon units, he only has to go through twice. Let's just write that equation down real quick. So the number of cycles is equal to the number of carbons. Divide by 2 minus 1. So 6 carbons divide by 2 is 3 minus 1 is 2. If you have a 6 carbons fat, you're going to go twice through the fatty acid oxidation cycle. If you have a 16-carbon fat, 16 carbons divide by 2 is 8 minus 1 is 7. So a 16-carbon fat will only go through the fatty acid cycle 7 times. Now, this is for saturated fats. Recall that saturated fats have no double bonds. We can also take unsaturated fats through the fatty acid oxidation cycle. Sometimes the position of that double bond a little bit less is to shift the position to this step. But in case the double bond is in the wrong position, all we have to do is shift it over. So we can use an isomerase to shift the position of that double bond into the right place. Now, we have basically the same molecule that we have here. And once we've got that double bond in place, the rest of the cycle is basically the same. So unsaturated fats are actually going to give us a little bit less energy, because the creation of that double bond, the oxidation guy, and we're going to add to it our 2-carbon acetyl unit. That's going to give us a 6-carbon guy. We are going to decarboxylate this guy twice, take a carbon off him twice. So we're going to create 5 carbons and then 4 carbons. And then in a series of isomerizations, we're going to return our 4-carbon guy here back to our original 4-carbon guy. Hence the cycle. Part of Krebs' cycle. All right, let's look at some names. We know our acetyl-CoA up here. Our 4-carbon guy at the top is called a oxaloacetate, or oxaloacetic acid, OAA. Useful to know because 1, he's the regenerated molecule, and 2, we're going to see this guy in gluconeogenesis as well. Our 6-carbon guy here is citrate, citric acid. Citric acid happens to have 3 acid functional groups on it, 3 carboxylic acid functional groups. So he's also known as tricarboxylic acid. And citric acid or citrate gives us the other names for the Krebs cycle. Krebs cycle is also known as the citric acid cycle, and is also known as the TCA cycle. TCA stands for tricarboxylic acid, TCA. Sometimes people think it means the citric acid cycle, but it doesn't. Tricarboxylic acid cycle. All right, so whether they call it Krebs cycle, citric acid cycle, TCA cycle, whatever, it's the same thing. All right, so we went from 6 carbons to 5 carbons. We lost a carbon as carbon dioxide. And we generated an NADH. And then we did it again. We went from 5 carbons to 4 carbons. So we lose another carbon here as carbon dioxide. And we generate another reduced electron carrier, another NADH. Now, in the process of back to oxaloacetic acid, we're going to produce a GTP. GTP is the energy equivalent of ATP. High-energy phosphate is high phosphate. We're going to generate an FADH2 and 1 more NADH. So Krebs cycle in this cycle DH couple of P made, and that's what happens. A bunch of electrons Na prove twice. So our net for Krebs cycle is 6 NADH, couple of FADH2s, couple of GTP.
Wait, Riva, are you running? Okay.
Let's write down our net. So pyruvate, we're going to net 2 NADH. Krebs cycle, we're going to net 6 NADH, 2 FADH2s, and a couple of GTP. So far, we've made a little bit of usable energy and a couple of GTP here in the Krebs cycle, couple of ATP, net ATP made during glycolysis. And we've reduced a bunch of electron carriers. What we'd like to do now is take these reduced electron carriers and make some usable energy. And that's what happens in the electron transport chain. Let's summarize to net 2 net ATP made during glycolysis. And we've reduced a bunch of electron carriers. What we'd like to do now is take these reduced electron carriers and make some usable energy. And that's what happens. To remember is that if you use carbon as carbon carrier, we're going to do this twice per glucose. Because we had 2 pyruvate at the end of glycolysis. So our net for pyruvate dehydrogenase complex is 2-NADH. All right, Krebs cycle. Krebs cycle, we're going to start with a 4-carbon guy. And we're going to add to it our 2-carbon acetyl unit. That's going to give us a 6-carbon guy. We are going to decarboxylate this guy twice. Take a carbon off him twice. So we're going to create 5 carbons and then 4 carbons. And then in a series of isomerizations, we're going to return our 4-carbon guy here back to our original 4-carbon guy. Hence the cycle. Part of Krebs cycle. All right, let's look at some names. We know our acetyl-CoA up here. Our 4-carbon guy at the top is called oxaloacetate, or oxaloacetic acid, OAA. Useful to know because 1, he's the regenerated molecule, and 2, we're going to see this guy in gluconeogenesis as well. Our 6-carbon guy here is citrate, citric acid. Citric acid happens to have 3 acid functional groups on it, 3 carboxylic acid functional groups, so he's also known as tricarboxylic acid. And citric acid or citrate gives us the other names for the Krebs cycle. Krebs cycle is also known as the citric acid cycle, and is also known as the TCA cycle. TCA stands for tricarboxylic acid, TCA. Sometimes people think it means the citric acid cycle, but it doesn't. Tricarboxylic acid cycle. All right, so whether they call it Krebs cycle, citric acid cycle, TCA cycle, whatever, it's the same thing. All right, so we went from 6 carbons to 5 carbons. We lost a carbon as carbon dioxide. And we generated an NADH. And then we did it again. We went from 5 carbons to 4 carbons. So we lose another carbon here as carbon dioxide. And we generate another reduced electron carrier, another NADH. Now, in the process of back to oxaloacetic acid, we're going to produce a GTP. GTP is the energy equivalent of ATP. High energy phosphate is high phosphate. We're going to generate an FADH2 and 1 more NADH. So Krebs cycle. GTP is the energy equivalent of ATP. High energy phosphate is high phosphate. We're going to generate an FADH2 and 1 more NADH. So Krebs cycle is big, right? 3 NADH, a GTP, and a FADH2. And we're going to turn this cycle twice per glucose, because each glucose resulted in 3 pyruvate, thus 2 acetyl-CoA. So we're going to turn this cycle twice. So our net for Krebs cycle is 6 NADH, couple of FADH2s, couple of GTP. Let's write down our net. So pyruvate, we're going to net 2 NADH. Krebs cycle, we're going to net 6 NADH, 2 FADH2s, and a couple of GTP. PD, so glycan transport and oxidative phosphorylation. These occur along the inner membrane of the mitochondria, and they actually use oxygen in the series of reactions. We say they have a direct need for oxygen. What you need to know for the cellular respiration pathways in general is the general carbon chain, where carbon is coming in and leaving and whatnot. Where energy is coming and energy is direct need that the in the anaerobic, it happens, oxygen. So glycan, the Krebs, if oxygen is not available, they can't run. So we say that these have an indirect need for oxygen. And then our final process, making a bunch of reduced In this video, we'll be discussing stem cells. Stem cells are effectively undifferentiated cells. These are cells that have the potential to become many different cell types in the body. They can also reproduce to make more stem cells. So they're pretty much an undying cell line, an immortal cell line. Stem cells are found in 2 main places. In the blastocyst, these cells here of the inner cell mass are called embryonic stem cells. These are the stem cells that have all the controversy around them in research and the like. And then we've got tissue stem cells. And these are found in different places in the body and the brain, the skin, the bones, gonads, intestines. These are less controversial, but more difficult to work with, because these are a little bit further down the differentiation pathway. So it's possible to take them and undifferentiate them back so that they can become more generic. But it's harder to work with them. It's easier to work with the embryonic stem cells. But these, of course, have all of those controversial issues surrounding them. So stem cells have to go through a couple of processes to become the other cell types that they will become. The first cell process is called determination. And determination is when the cell becomes committed to a particular fate but hasn't gone through the physical changes to become that cell type yet. So this is a cytoplasmic occurrence, and this is something that happens in the cytoplasm. It says to the cell, you're going to be a neuron, and you're going to be a muscle cell, and you're going to be... So at this point, the fate of the cell is determined. This is an irreversible process. The next step is for the cell to actually go through those physical changes, and that's called differentiation. So in our diagram up here, determination precedes differentiation. The cells of the inner cell mass are known as pluripotent stem cells. Pluripotent means that you can become any cell in the body, but you can't become the outside the embryo things. You can't become the placenta. Tissue stem cells are even more specialized. They also have to go through a process of determination and differentiation, but they can become fewer cell types. Because again, they're already further down the pathway. So these cells are known as multipotent cells. They can become many of the cell types in the body, but not all of the cell types in the body. The only cell in the body that is totipotent can become anything, the body or the placenta or the extra embryonic structures. That's the zygote, and maybe a few divisions after the zygote. Some books go so far as to say up to the morula. The morula is still totipotent cells. And certainly, we see it in some cases when the zygote divides and you've got two cells. And then, for whatever reason, those two cells develop independently, and you get identical twins. So clearly, the early stages, 2-cell stage, 4-cell stage, these are still totipotent cells. But at some point, like Blastocyst, they're no longer totipotent and only pluripotent. So totipotent means, again, that you can become any cell in the body as well as the placenta. Let's summarize what we talked about in this video. We looked at the location of stem cells in the body, either those embryonic stem cells as part of the blastocyst or the tissue stem cells kind of distributed. We talked about the processes by which a stem cell becomes a mature cell in the body. So determination and then differentiation. And lastly, we look at the classification of stem cells, either totipotent, becoming all the cells in the body and the placenta, pluripotent, becoming any of the cells in the body, or multipotent, becoming a subset of cells in the body.
I'm pretty sure that's relatively low yield. Gosh, oh, Genesis.
In this video, we'll be discussing the female reproductive system, specifically the function of the ovary and oogenesis.
monkeys on stem cells?
The ovary is the female primary sex organ, and like the testis, the male primary sex organ, it has two jobs. The ovary's jobs are to make ova, or eggs, and to make estrogen and progesterone, female sex hormones. The process of developing eggs is called oogenesis, and the counterpart to oogenesis is spermatogenesis. Now, spermatogenesis takes place on a daily basis, with many sperm being produced daily, 4 mature sperm being produced per precursor cell. Oogenesis is spread out over a much longer time frame with 3 distinct phases: one that happens before birth, one that happens during the majority of a woman's life, and then one that only happens if the egg is fertilized. So the stage that happens before birth is the prenatal stage. And during the prenatal stage, oogonia, that's the counterpart to spermatogonia, reproduce by mitosis to form more oogonia. And this will go on until you get about 200,000 to 400,000 oogonia. Those oogonia are then activated to form primary oocytes. And the primary oocytes are then arrested. They begin the process of meiosis, but they're arrested very early in metaphase. So the process pretty much stops at this point. Then, they'll stay in that arrested state for decades. The next state doesn't begin until puberty about. This is on a monthly basis, beginning with the first menstrual cycle, called menarche, and ending with the final menstrual cycle, called menopause. So puberty and menarche are not exactly the same thing. Puberty can start about a year or so before the first cycle happens. So we say menarche to menopause, roughly 40 years. If menarche is typically around age 12 or 13, menopause in the early 50s. So you're looking at about 40 years of fertility. So, on a monthly basis, a few of those primary oocytes will go through meiosis 1. So about 5 or 6 of them start the process, but only one of them really succeeds. The guy who is the most mature when the signal for ovulation comes is the one that is released, and the division is not equal. We don't get 2 secondary oocytes from this division. One of the cells gets all of the cytoplasm and all of the organelles. That's the secondary oocyte. And then the second cell is just a little package of DNA called the first polar body, so from 5 or 6 initial cells, only 1 secondary oocyte is produced, sometimes 2. Sometimes there's a double ovulation, but typically there's only 1. The secondary oocyte is ovulated, and then the process stops again. Now, if that oocyte is fertilized, then the final stage of oogenesis will occur, and that is the secondary oocyte will go through meiosis 2, and again, the division is unequal. So you're not going to get 2 ova from this. One of the cells will get all of the cytoplasm and all of the organelles, that's the ovum. And the other little cell is essentially just a small packet of DNA, the leftover DNA. And that's the second polar body. So from 5 or 6 precursor cells, we're going to get 1 secondary oocyte. From that 1 secondary oocyte, we're typically just going to get 1 ovum. So this is different than spermatogenesis. In spermatogenesis, we got 4 mature cells from a single precursor. Here, we're getting 1. So most fertility drugs work here to increase the number of primary oocytes that begin this process. So instead of starting with 5 or 6, you're starting with about 15 or 20, which means that you're going to have more guys ready to go. So if you're starting with 15 or 20 here, you're going to end up with maybe 4 or 5 secondary oocytes. This is why fertility drugs often result in multiple birth pregnancies. So oogenesis spread over 3 distinct stages that does not occur for the entire adult life of the female. Only about 40 years here. We do not have an unlimited supply of precursor cells, and we get one mature gamete per precursor cell. Let's summarize what we talked about in this video. We looked at the functions of the ovary to produce ova and to produce female sex hormones. And we looked at the process of oogenesis, comparing it to spermatogenesis. Secondary oocyte. From that one secondary oocyte, we're typically just going to get one ovum. So this is different than spermatogenesis. In spermatogenesis, we got 4 mature cells from a single precursor. Here, we're getting 1. So most fertility drugs work here.
I need to work on stuff. I need to work on another class before I sleep, because hopefully I can finish by 10:30, because I need to get up early tomorrow to write an essay. So